Okay. Thank you very much, first of all, to the organizers of this conference, to the generous people that provided funding, to Kevin for his role in organizing, and also for teaching me something very important that is going to come very handy today, which is the fact that in philosophical conferences, the tradition is that you only ask questions afterwards, and that's going to be enforced strongly and strictly during my talk. In particular, because I have a lot of material to cover, but afterwards I will be very, very happy to talk to you about and answer as many questions as possible. Okay,
We should note he is going for a whole hour, so you'll have to ask him at dinner.
Okay, so the plan of the talk is I'm going to talk about a little bit more about the quantum measurement problem in gravitational context. I'm going to say a few words about how we explore the quantum gravity interface and how I think we should explore the quantum gravity interface, at least in a particular approach. Then I'm going to talk a little bit about the inflationary account of the emergence of the seeds of cosmic structure and these features that we now see in the CMB, the big success of inflation. I'm going to mention something about the tensor modes, which are a feature that is giving some problems, at least to the simplest models of inflation. And then I'm going to jump into something that Professor Starowinsky mentioned, that is the connection with the things like black hole information and so forth, and make some final considerations. If I had half an hour more, I would be able to tell you about some other very interesting stuff. Okay, so as we have learned in the talks, particularly the talks yesterday, and in particular Daniel Oriti's talk, it's very hard to think about physics without space-time, without having space-time, and furthermore adopting a clear view about what quantum theory says about the world makes things even harder. And my point is going to be that generically this we fail to do that. We fail to adopt a clear view, and that leads to all sorts of confusions. And one of the confusions, the classical one, is connected with the notion of fluctuation. It's a word that unfortunately is used to refer to at least three different types of things, and is nevertheless used by most physicists as if they were the same thing. So one of the meanings is variations through space or through space-time of some well-defined attributes of an entity. Let's say the surface of the water, we say there are fluctuations from place to place and from time to time. Another thing is variation of the well-defined quantities within an ensemble of systems or of similar systems. Variations for instance, let's take a thermal collection of classical harmonic oscillators and consider their canonical ensemble. There are fluctuations there. Each particular element has a well-defined energy. Nevertheless, there are fluctuations which refer to the variations within the ensemble. And finally, there are quantum indeterminacies or quantum uncertainties, which are also referred to with the word fluctuations. For example, the fluctuation in the position of an harmonic oscillator in its ground state. I have one harmonic oscillator in one particular state, and nevertheless there are fluctuations, and what it means is that the position is not well defined, and I should never think of this as indicating that somehow the harmonic oscillator is jumping from one point to another point. A connected issue that appears in physics is the failure to distinguish between proper and improper mixtures, and philosophers, I'm sure, are very clear about this, physicists not so often. Moreover, we should also try to be clear as to whether the fluctuations we are talking about are ontological of the type 3 conditions, for instance, in our universe, or epistemic, for instance, the quantum state of our universe, taken as selected from some imaginary ensemble of type 2. Confusion of this type frequently leads to problems. One example is a program called stochastic gravity, which is based on somehow the idea that you could simply correct semiclassical gravity by adding something that represents the fluctuations of space-time, and this object is introduced as a classical stochastic tensor. That happens that is selected with certain properties and is supposed to represent these fluctuations, these quantum fluctuations. One of the problems is that while on average, as was being mentioned before, these objects satisfy divergence of equal to 0, it does not satisfy divergence equal to 0 for each individual element of the ensemble. So you have a collection of inconsistent equations, and you hope that somehow the average of inconsistencies will lead you to something that is consistent. This problem is often not appreciated, and of course these problems appear often traced to the tendency to ignore the M problem. Now this letter has become very popular, and I'm going to adopt it for this issue. The M problem is the measurement problem or reality problem in the quantum theory, to which Elias mentioned, referred in his talk. So we will approach now the exploration, in view of these things and of the previous talk, we will approach the exploration of the interface between gravitation and quantum theory in a top-bottom approach. The usual approach, the usual strategies of dealing with this is to postulate a fundamental theory, usually a fundamental theory involving quantum gravity, for instance string theory, loop quantum gravity, causal sets, and so forth. And one then does a lot of work trying to connect that theory to the world out there and describe cosmology, black holes, etc. We are going to adopt the opposite approach, which in some sense can be thought as complementary, which is to push existing theories that are well tested to address issues that are often thought to lie outside the domain, and to push and look precisely to places where there is collisions, to try to look for clues about what is the nature of the fundamental theory. So in our case, we are going to try to push GR together with quantum field theory, that is semi-classical gravity, into realms that are usually not explored. We should do this, or we should try to do this, sticking to a concrete and fixed view regarding the ontological meaning of quantum theory, to make sure that we don't fall into at least internal inconsistencies. Since we have seen it's very hard to talk about pre-space or physics in pre-space-time context, we will work in regimes in which we think.
There's a question.
There is no question.
You really want to enforce no questions?
Yes, I will.
But
I will enforce.
But if we cannot follow, then there's no point that you go on if we have questions. Then...
Ask a question, please.
Right. So you want to work in the context of semi-classical gravity?
Yes.
I can give you a tabletop experiment which shows that semi-classical gravity doesn't work.
That's the talk was that was what was taught in the talk before. That was described in the talk before. Precisely. Okay. So I'm going to say precisely what it works. Okay. So we are going to work in this context in the regimes where curvatures are not large and quantum uncertainties are also not too large. Matter will be treated quantum mechanically, and in that context it's natural to identify the local-beable as the quantity that produces the curvature of space-time. That is somehow the energy momentum tensor. And of course, we just learned that we have a problem because, as Elias said, all approaches to dealing with the measurement problem leads to generic violations of conservation of energy momentum tensor. We take this view as provisional because we don't expect the theory to be the fundamental theory of nature. As I said, we're working in a bottom-up approach, which means we are dealing with this theory as an effective theory and not with a fundamental theory. We expect the fundamental theory for there to be something in which space-time is described quantum mechanically and perhaps in a non-space-time kind of language. Therefore, space-time will be emergent in our view. Okay, so regarding the end problem, we will concentrate on theories involving spontaneous collapse theories. As was mentioned before, there is a large amount of theories, of work on this type of theories. The basic idea of these theories is that they unify in a single dynamic, in the single equation, or in a single dynamics, both the unitary evolution and what is normally called the reduction processes. The changes of the theory are very, very small when you have very few degrees of freedom involved. They become very large when you take a very large number of particles and entangle them. Then the localization process becomes very, very effective and works very, very quickly. So the theories have been constructed to be empirically viable in the non-relativistic, at least in the non-relativistic context. But in our situation, we will concentrate on on an ontology that is centered on, as Elias said, identifying the expectation value of the energy momentum tensor as the fundamental local-beable. It's important that we should not think of this as an average, but as the actual entity that exists and that curves space-time. So in some sense, it's a general relativistic version of the mass density of mgrw. Okay, if you've never seen one of these theories, this is a theory, spontaneous localization. This is an example of the theory we will encounter in several occasions here. It corresponds to a modified Schrödinger equation. So the evolution of a system that is initially preparing this state will evolve according to the standard part, plus a correction term that contains three objects. It contains a random classical variable. It contains a collapse operator that tells us select into which kind of states will the theory collapse the system. And it has a fundamental parameter that tells us about the rate, how often these collapses occur, and is supposed to have a range of the order of 10 to the minus 16 seconds. So it would, something like that would mean an electron will collapse 10 times during the age of the universe. The theory is being experimentally tested, so there is a very serious program studying this thing. Nevertheless, how do we deal with our problem? Our problem was the problem that if I put collapses into the theory, things semiclassical gravity breaks down. So I'm going to start by defining something I would call the semiclassical self-consistent configuration, which is nothing more than a space-time, a classical space-time, the construction of a quantum field theory on that space-time, and a selection of a particular state in that Hilbert space such that this equation is satisfied. So the theory is internally self-consistent. Of course, the whole construction of the quantum field theory depends on the metric, but the metric is constrained by the construction and by the selection of the state in this way. This is some kind of general relativistic version of the Schrödinger equation. Now, let's think about the collapse. A collapse would be a transition from one complete SSC, self-consistent configuration, to another one. Because if the state jumps, then the metric will ingenuitively jump, but if the metric jumps, your whole field theory construction needs to jump, and you need to do this in a self-consistent way. We have done this in several concrete examples. So, the idea is to have, while we will have this formal thing in view, this formal scheme in mind, while working, we will, in the actual applications, proceed in some with some tools that allows you to go faster and to do the actual calculations. So let me go, for instance, to inflation. Contemporary inflation, as we've learned this morning, is a very successful part of current cosmology, and its most spectacular success is supposed to be the account for the seeds of for the birth of the seeds of structure as a result of quantum fluctuations, and it turns out that the spectrum one obtains in this way is correct. However, at the theoretical conceptual level, the account is truly not satisfactory. I will explain precisely what. Let me start the analysis with this metric corresponding to a cosmological Friedman-Robertson flat spacetime, in which I have added, first of all, I have chosen a specific gauge, and I have added the two most important perturbations, which are the scalar and the tensor perturbations. And we normally start with a scalar field that is divided into a part that does not depend on space, and a spatial dependent part. The background is given by the particular case in which these perturbations are all vanishing, and if we're in the slow roll regime, and the potential dominates the energy of the zero mode, then the metric is completely described by the scale factor that satisfies this equation. And inflation is supposed to last a finite amount of time, but producing enough number of defaults. And then the perturbations, these objects are treated quantum mechanically and assumed to be characterized by the vacuum state. Normally the bunch state is vacuum, but as Professor Starobinsky mentioned this morning, it should better be called the adiabatic vacuum. The important point about this vacuum is that it's completely homogeneous and isotropic state. And that is natural, because the basic idea of inflation is that inflation dilutes all persistent features and drives all space-dependent fields towards the vacuum state. But this field is also characterized by quantum fluctuations. And here we have one instance of that kind of confusion. The uncertainties and quantum indeterminacies associated with certain operators in that particular state are now called fluctuations, and are identified as fluctuations of type 1. That is, fluctuations over our universe, which eventually grow and evolve into galaxies, stars, planets, etc. However, as I noted, the universe is described at this stage by something that is completely homogeneous and isotropic, both at the classical and quantum level. In particular, the quantum state can be easily seen to be homogeneous and isotropic. Simply applying a displacement or rotation operating on the field, you obtain the same state. But of course, the situation at the end is a situation which is not homogeneous and isotropic. There are stars, galaxies, so forth. How does this happen if the dynamics of the closed system does not break symmetries? our approach can deal with this problem. As I said, space-time is going to be treated classically, and the scalar field must be treated in the quantum field theoretical manner. In this case, we should, even the zero mode should be treated quantum mechanically, and we will use now semiclassical equations, which, as I forgot to mention, in the SSC scheme are equations that are valid in between the collapses, but not during the collapse itself. So you have an SSC that describes a region, a space-time and a quantum field theory before a collapse, then you have a collapse on an hypersurface, and then you have to glue it to another regime in which you have a separate SSC, and this is what we have in mind happening here. So the classical background, of course, satisfies writing the semi-classical equation. One obtains basically the same behavior for the scale factor and the zero mode of the scalar field, which is supposed to be in a highly excited coherent state. But the other modes, the modes that have space-time dependence, are all in the vacuum state. And as I said, we will rely on a practical procedure that we have checked to give equivalent results to the SSC formalism in the schemes, in the situations in which the second one work. So in the early stage of inflation, the state is the vacuum. The fields, the Fourier components of the field and momentum operator are characterized by Gaussian wave functions, centered at zero with uncertainties that you can compute. However, semi-classical equations will give us both metric perturbations equal to zero. The collapse will lead to a change in the state, and therefore a change to the expectation value of these quantities. We will assume now, for simplicity, that the collapse occurs mode by mode, and our universe will correspond to one specific realization of this stochastic, the stochastic functions controlling the collapse. If we concentrate first on the scalar perturbations, then one can write Einstein's semi-classical equations takes this form. So now, if the state collapses and this quantity acquires a non-zero vacuum, a non-zero expectation value because it's not longer in the vacuum, now there is a corresponding excitation of the metric potential. If you choose the collapse operators appropriately, one can recover basically the standard result, except for, I mean, here we have the V is the potential of the inflaton, so these are the standard forms, and here we will have something else. This is the number of this is the conformal duration of the inflation and this is the parameter controlling the collapse. If we use GAT scale for the inflaton's potential and standard values for the slow roll parameters, one can find out what is the implied value of this parameter lambda, so that you recover the correct amplitude for the power spectrum, and the number we get is 10 to the minus 19 seconds to the minus 1, which surprisingly is not very different from the GRW prediction. Okay, there are other treatments have been done, and depending how you select the collapse operators, you get or do not recover data. Okay, this is fine. We have adjusted the collapse operator so that our theory fits the data, you could say. But now we can do the same with the tensor modes. And the tensor modes turn out to behave very differently, because in the tensor modes, the source of the tensor modes is the ij component of the energy momentum tensor, which of course needs to be renormalized. And that leads, if you go to the Fourier, you do a Fourier transformation and you write an equation, leads to a complicated problem that nevertheless can be integrated. We have integrated this quantity and obtained the quantity is formally divergent. You need to put a cutoff by hand. It's not difficult to think of reasons why there should be a cutoff. In particular, we know that there are effects, diffusion effects like silk damping and so forth. The point is that at the end, you compute the spectrum of the tensor perturbation, and you obtain something that is dramatically different from the standard calculation. In the usual approach, the relationship between the scalar and tensor perturbations, they are basically the same. They differ by this slow roll parameter or something like that. But here we see that the difference is dramatic. Here, this is quadratic in the inflaton potential, while this is linear in the inflaton potential. So the prediction for tensor modes in this scheme is completely changed from the standard one. This is the standard prediction for the tensor modes that one obtains in the usual treatment of inflation. This is the prediction we obtain in the CSL model I just have used. This is a prediction one obtained in a different theory of collapse theories, a different type of collapse theories. The generic feature is that there is, first of all, the spectrum is at a much lower level, and it has also a different shape. Okay, how am I doing in time?
25 minutes?
I have left 25 minutes.
Including questions?
No.
No.
All right.
Because there are no questions.
No, at the end there can be as many questions as you want. I'm willing to stay here all night. Okay, so black hole information. Black hole information. The black hole information problem is the result of, or consequence of the fact that quantum field theory effects called the black hole to makes the black hole radiate, and it should lose mass, and if this process continues, basically it's a runaway process, the black hole eventually disappears, leaving just thermal radiation, or perhaps a small remnant, which I will not mention here. And then one is over here as well. Quantum theory requires a unitary relationship between initial and final state, but that is true only if one is considering states on full Cauchy hypersurfaces. And note that here, while scribe minus could be said to be a Cauchy hypersurface for, well, Cauchy hypersurface for at least the past region, is certainly not a Cauchy hypersurface. Scribe plus is certainly not a Cauchy hypersurface. So people often demand or require a unitary relationship between the state in scribe minus and the state in scribe plus, and this is both unwarranted and, moreover, very hard to account for. Enormous amounts of efforts have been devoted to this thing. So, beware, the black hole information paradox arises only if one assumes that quantum gravity cures the singularity and the need to add a boundary to space-time. Here, we have in some sense added this other boundary of space-time that we have called the singularity. It's only if quantum gravity replaces this singularity by something non-singular that you really face a problem. Otherwise, one would easily adopt the postures of Bob Wald, or the modified posture by modeling, changing the notion of Cauchy hypersurface, or extending the notion, and then there is absolutely no problem. But then, if this is the case, if quantum gravity solves and resolves the singularity, then then one faces the question of unitarity, because assuming there are no remnants, we could have started with a pure state, and at the end we have thermal Hawking radiation. But wait, quantum mechanics also involves some departures of unitarity, in particular in connection to measurements. And this brings us back to the M problem. So in theories of spontaneous collapse, departure from unitarity from unitary evolution is present in general. And this, in these papers, we suggested that this may be used to deal with the problem, the black hole information problem. So the idea is to see if one can come up with a picture in which the two types of departures from unitarity are unified. We have actually done this in explicitly computing everything in detail, but in two-dimensional models, where is the kind of model in which you can actually, perform calculations. So this is done in this paper. Let me go quickly over this. So we need to do a quantum field theory in a black hole spacetime. One does quantum field theory in curved spacetime treatment of the matter fields. First, in the in region before the black hole forms, uses the Heisenberg picture, and the state of course remains fixed. The state doesn't change. The field operators evolve, and so the evolution is encoded in the quantum field. The initial state, which is can be written schematically as, let's say, the zero, the vacuum for the test matter field, and a matter pulse that is going to collapse and produce the black hole. And then one describes the same state at late times, separating the description appropriate for the internal part of the black hole and the external part of the black hole. So perhaps I should draw a map. So the idea would be that somehow quantum gravity resolves the singularity. So we have matter collapsing, and I'm going to now describe the state here, and normally one describes the state here in an hypersurface that goes like this. If nothing happens in between, the state is basically the same state, but is described in different coordinates. And in describing this field in the different coordinates, one needs to describe the state in terms of modes that exist in the outside and modes that exist in the inside. And then the vacuum, it looks like this one, a state highly correlated between the inside and the outside. If I did trace over, if I computed the density matrix of this thing and traced over, one would be led to this improper thermal state. So a density matrix that now represents an improper mixture and not a proper mixture, which should not be confused with. The complete state now can schematically be written in this form. This is the state of the vacuum, and this is the matter pulse that certainly has evolved. But now we will consider the evolution. This is what happens without the collapse theory. So now we will consider the evolution using the modified dynamics provided by CSL type theory. And we are to apply such theories, one needs to foliate space-time by some time parameter. We're going to use a time parameter which, for reasons that will be understood in a moment, will correspond in the interior region to hypersurfaces of constant Weyl curvature in the interior, and anything that goes to I naught in the outside. That is not relevant. And now I'm going to choose the collapse operator. So I have a collection of modes, so I'm going to choose a collection of a collapse operator, one for each mode. And I'm going to assume that the modes that are going to be most strongly affected by the collapse are the modes of the field in the interior. And I'm going to assume, and therefore the states will collapse to approximate states of definite number of particles in the inside region. These particles are, formal particles in a sense. Since we're working in the interaction picture, the Hamiltonian will disappear from here. It's zero because all the evolution is encoded in the fields. But now I'm going to work in the interaction picture by bringing the non-trivial part of the CSL dynamics, the modified part, and treat it as an interaction. When I treat that as an interaction, the states will now evolve. I'm going to assume that the collapse operator, instead of being a constant, is modified by the gravitational environment. The the proposal is that it takes this form well, actually should be doubly here. So the collapse operator now depends on the local value of the curvature, in this particular case the Weyl curvature. And I need to do that to ensure that in the finite time that my state, that my hypersurface reach the singularity, or the region that would have been the singularity, a collapse has been achieved, which normally with a constant lambda takes an infinite amount of time under normal conditions. So this is the modification we have to do to the CSL theory to ensure that our approach works. If that happens, then I start again with my initial state, which I write in this form, and the state now is evolved by the CSL dynamics, which, as I said, will achieve in the finite time to a region very close to the singularity, a full collapse to one of the eigenstates of the internal modes. So this is going to be the state out of the field in this hypersurface over here. It's a pure state. There is no summation. The evolution has been from a pure state to another pure state. So we don't know which one. And here is where the difference between proper and improper mixtures is going to play a role. But now I need to assume a role for quantum gravity.
14.
How many?
14.
14 minutes. Okay, so now I have to say what happens here. I now want to describe the state on the other side of the singularity. Notice that I had a lot of positive energy going into the black hole coming from the matter field here. I have most of the energy in form of radiation going out here, and the corresponding negative energy flux coming in here, which actually goes like that. Okay? The point is that if I consider this region, and the violations of energy momentum conservation are not too large, this part should have very, very little energy left. To make things simpler, I'm going to assume that that the evolution of the state from that hypersurface previous to the singularity to the post-singularity or post-quantum gravity region takes that region that has basically no energy to actually something I will call the vacuum, the post-singularity vacuum. This need not be exact, but makes the analysis much simpler. The point is that at the end, my state is simply a collection of particles outside and nothing inside here. But now I consider an ensemble. I prepare an ensemble of identical states with the pulse and the vacuum initially, and now I describe the density matrix of this ensemble, which is nevertheless pure because they have all been preparing the same state. I now evolve this density matrix in the way I said, and taking into account the weights with which the different components appear in my pre-collapse state, what I obtain is basically the vacuum for the region post singularity plus a thermal state outside here. So we started with a pure state, ended up with a proper thermal state characterizing this ensemble that I made. Information was lost as a result of the general quantum evolution, of course modified by the collapse theory, and of course there is absolutely nothing paradoxical here. Concerns, energy violation, some early concerns about theories that would involve something like this were raised by Banks, Susskind, and Peskin, but further analysis by Unruh and Wald indicated that those were exaggerated. The argument was that the energy violations would be huge, and the energy violations, according to as Wald and Unruh showed, could be made to be small. Actually, dynamical collapse theories have been constructed to ensure compatibility with experimental bounds. Some of the most stringent experimental bounds precisely look at the self-heating of things like Bose-Einstein condensate. So people take a Bose-Einstein condensate, make sure they isolate it sufficiently, and look if it self-heats. So this is related to the question that was asked earlier on, if we could use this as a method for generating energy. The problem is that these theories tend to generate energy in a very disordered type, so it would become heat, not very particularly, but in principle it could be used, but it's not, you don't go and just charge your battery directly. On the other hand, this energy violation, if it's occurring all the time, needs to be dealt with. And in the cosmological setting, we have seen that the cumulative effects of violation of energy momentum in a slightly modified theory of gravity called unimodular gravity that allows certain types of energy momentum conservation, one generates a cosmological, automatically from the theory, from this non-conservation, one generates something that behaves like a cosmological constant, which happens to have the right order of magnitude. So I invite you to look at this paper, where you will see that one obtains naturally, without any type of fine-tuning or adjusting of parameters, the observed, well, a value of the order of magnitude of the observed quantity for the present-day cosmological constant. Other issues, foliation dependence, well, in this particular scheme that we have used a non-relativistic version, this should be eliminated by passing to a relativistic version. Actually, we wrote the paper with the author of one of these relativistic versions, Daniel Bedningham, again in two-dimensional versions, in which we incorporated that type of dynamical collapse theory and accounted for black hole information loss in a similar way. The program has more potential. Apparently, it may offer a potential solution to the concern called eternal inflation. It may offer a path to naturally explain the anomalous low power at low L's that some people in inflation are concerned with. Appears to have promising, it's promising, we have not really developed this idea much, but for dealing with the problem of time in canonical theories of quantum gravity, but of course there is a lot of work ahead. The whole approach could, of course, be wrong. It could be shown to be non-viable by something that we have not yet noted. But here I want to quote Sir Francis Bacon, considering the recommendations for the scientific enterprise in general. His statement is, truth emerges more readily from error than from confusion. And that, I take it here to be the following. We are being very specific, very clear, very direct to what are our assumptions, what is the ontology we are talking about, how things should be interpreted, and have proposed an approach to deal with concrete issues within that setting. It may be wrong, but we will discover it if it's wrong, because things are specific, are clearly stated, so there is no confusion. If you, on the other hand, have not made a commitment to any particular interpretation of quantum mechanics, if you don't make a commitment to a particular ontology, you may do a lot of work, but it will be very difficult for you to discover if you have made a mistake or not. So we believe that ignoring the measurement problem in the application of quantum theory to macro problems, in particular to cosmology or black hole physics, like like the situations I have just referred, is a source of potential, of enormous potential for confusion. Of course, that's not the case if one works and just is interested in applying quantum theory in the lab, where it's clear what are the measuring devices, when and who did the measurement. Thank you very much.
So have at least 15 minutes for this.
No, well, okay, I can only repeat Robert's remark that in the standard approach we don't use semiclassical gravity. We actually go beyond what actually follows from the field theory in that space-time. So, once more, gravity is quantized, and it follows from operator equations, and in particular that part with the average, the standard prediction both for scalar and tensor perturbation is that the average value is 0, but this does not mean that perturbations are absent. It simply means that it is equally possible to have plus some value and minus some value.
If I had time to ask a question during your talk, that would have been precisely my question. You said that the fact that the expectation value is 0, it indicates that you could, at any particular point, you could either have a fluctuation up or down in the density. And I wanted to ask you, what interpretation of quantum mechanics are you used to make that statement? Because without making an interpretation of quantum mechanics, you cannot, support that statement. That statement is based on some particular idea that you must specify, and you haven't, regarding what quantum mechanics says. So let me finish the answer, please. So if you have an harmonic oscillator, you have to tell me, for instance, if you have an harmonic oscillator in the ground state, and if you don't make any measurement, is the harmonic oscillator equally likely to be on the right or on the left-hand side of the potential? Is that your interpretation?
Okay, once more, it's a property, so I shall answer your first part of your statement. It's a property of the squeezed quantum state, and squeezed quantum state, not only it's a theoretical construction that's interesting, but now it's actually used even in gravitational wave detectors.
That doesn't change the symmetry. That doesn't change the symmetry.
No. Okay. Once more, I repeat that. This is the property of squeezed vacuum quantum state, which, as I said, is actually used. So that's what we can actually measure are calculation functions. But I agree with you that indeed this means this result, as usual in quantum mechanics, is independent of the interpretation, but I would say it's an extended example of the Schrödinger cat. So the only difference is here the situation is more complicated. In case of Schrödinger cat, we have a superposition, say, of two states with say plus y and minus y, and here the prediction that we have a whole range of continuous values for
fine, but if you don't say how you resolve the Schrödinger cat,
Well, let me follow up on this.
you cannot. Let me answer.
Okay,
let me answer. No.
Okay,
Let me answer.
it's just
If you don't,
okay.
let me answer. Can I answer?
Indeed, due to the coherence.
No, the coherence does not solve the measurement problem. That is a widespread misconception among physicists. It's very clear that it does not work. Is it very clear that it does not work? I can give you a concrete example of how it can be seen that it does not work.
Let me
But
follow
yes.
up on this. What it's
Yeah,
doing for
the-
scalar and gravitational waves is exactly what one does in a laser. One is using a squeezed state. So I agree completely what Alexei is saying.
Fine, I have absolutely no problem. You have a squeeze state, and in the squeeze state, you have changed the relationship between the uncertainties in the momentum and position to some other variables. And if you look at the uncertainties in momentum and position in the squeeze state, they remain in the same. This is a standard harmonic oscillator. This would be the uncertainties in Q and P on a squeezed state, with very interesting correlations, however. Nevertheless, for anisotropies to arise in the universe, you need to tell me that somehow I pass from that state to something like this. In this globe, which everybody knows, there are definite points which are hotter and colder. And they became hotter and colder before anybody made a measurement. So this is very different from what occurs with what we do with the squeeze state in the lab. With the squeeze state in the lab, we do very interesting things, but one thing we do is make measurements. And when we do make measurements, we change the state in all sorts of ways. Here, we have a state that is not homogeneous and is not isotropic before anybody made a measurement. And that completely distinguishes the situation we are facing here than the situation one faces in the lab when one makes a measurement.
Once more, as I said, indeed, due to, let's say, I can only repeat that due to
No, why did you repeat?
coherence,
We have heard.
due to the coherence, indeed, some actual anisotropies.
That's incorrect.
Okay.
That's incorrect. And let me answer why.
Okay.
Let me answer. Can I answer, please?
But let
No.
me,
Sorry.
let me
Can I answer or can I not answer?
let me finish. But
Go
in
ahead.
the problem which I showed that the predictions for all calculation functions are independent of the, or the fantastic accuracy they are independent of both the coherence of both the coherence process and interpretation of quantum mechanics. So once more.
So what's your interpretation of quantum mechanics? I ask you. What is your interpretation of quantum mechanics?
Well, answer that just as almost all things which you find in the textbook.
Yeah, you have written several several papers and several textbooks, and I have refuted them.
Predictions are independent. In particular, the predictions of the spectra of all transition states were independent of the interpretation of.
That's false. That's a false statement.
Okay.
So in the interest of time, Nick also has a question, so... Yeah, let me get the numbers. So, this was turning to the black hole models.
Yep.
So that's kind of a nice kind of picture of what's going on. So there's this other way of seeing what the paradox, the information paradox is, that really doesn't require you to go to the singularity at all and sort of solve it the way you're talking about. Rather, there's the sort of the standard picture, and I understand what you're doing. I didn't say anything yet.
No, you said it's not a picture. I'm just writing it for you.
Okay.
Is that's what
So in a standard approach, we're going to understand understand the thermal nature of the radiation coming out, because it's entangled with degrees of freedom that are inside the black hole.
Right.
But the black hole's evaporating, it's getting smaller, the area's going down, the Bekenstein entropy is decreasing, so there are actually fewer states inside the black hole with which to entangle, and so there's a limit to how much of what the entropy of the, how much thermal radiation there can be outside. That's decreasing while the amount of thermal radiation is going outside, right? And so we have the page-time paradox where there's not enough states inside anymore. So I'm wondering so my question, and this is supposed to be, there's no kind of agenda behind this, I guess.
No,
I'm wondering, it wasn't clear for me in the approach that you have, whether you can address that, and in particular whether it's sort of detailed enough that you can calculate the entropy of the black hole, and is it the Bekenstein entropy?
Well, we have not done the calculation that you say. I think it's a very interesting calculation. I think in principle our approach has the possibility of addressing the page paradox, because as I said, collapse is occurring, it's starting to occur. Well, it's occurring here also.
Yeah.
Only here outside is occurring at the normal rate, which is very small. It's not enough. Collapses are starting to occur here where curvatures are starting to grow. And as you start to approach here, they become very, very, very intense. So I can imagine that by the time you reach this, let me say this is the hypersurface corresponding here to the page time. So I could imagine that by the time that I reach this hypersurface, I have collapsed here enough that I have destroyed enough information to account for, you know,
So it's a
but we haven't done that calculation.
Yeah. But it's a real question for this model and something that would test it, in your opinion.
Yeah, of course, our calculation can be done explicitly only, or we have done it explicitly only in two-dimensional models. But yeah,
Okay.
we could in principle take our model and do that.
Okay.
Let me just,
We've got about 5 minutes left, so.
so let me explain why Bitcoin.
We don't have 5 minutes.
It's,
We have like
it's a
1
Q&A.
minute.
The buses.
The buses are
leaving.
yeah.
The bus has been here
We got
already
it.
and is leaving. So it's not a question of just
So I have 1 minute.
-2 minutes.
Yeah.
Make it 2 minutes.
-3 now.
This is a singlet state of an EPR pair. This is a singlet state of an EPR pair. It's rotational invariant around this axis. If you look at the spin projection in this direction N1 and the spin projection in this direction N2, there are correlations that go like the cosine of N1 times N2. These are the famous correlations, the famous Bell correlations. When you do measure and produce and project the state into some particular direction, the state does not longer have the symmetry. But before you measure, the fact that there are correlations there has absolutely no effect on the symmetry of the state and on the physical situation. If the state was symmetric before you computed the correlation, the state continued to be symmetric after you computed the correlation. Nevertheless, you can decide to trace over the degrees of freedom of particle number 1, and if you do that, the density matrix, the reduced density matrix of particle number 2 is just 1/2 times 1, 0, 0, 1. Perfect decoherence. Does this decoherence mean that somehow this particle has a spin up or a spin down and that the symmetry has broken? No. Precisely the same situation applies to the cosmological setting we were talking about. Thank you.
Let's